Hi everyone, this is Gustavo from Divergence AI, and I wanted to show you a little bit of the progress that we're doing for the next release of our Copilot. So we're going to load up our trusty dipole example in here, and I have the graphical version open for you to see what's going on, but this is our thing, and we have extracted the metadata from this design. And what we're working towards is the ability to give the user more capabilities to extract data from the simulation. So one example is to get actual variations. So we have, for this design, we have a parameter sweep on the parameter, the dipole radius. So for example, you can ask what variations are present in this project. And now our processing agent can quickly search and tell you, okay, well, here we go. I wrote some code and it says we have a sweep that has 14 parametric variations for DR ranging from 0.25 to 0.6. And actually, if you look at the notebook output, you can see each of these variations individually, just in a more messy way. You know, you might want to ask, for example, now plot S11 for all the variations, In this case, the agent is going to say, okay, well, now that I know that I have all these variations, maybe let me extract data from each of them. So this is what you see happen right now, that it wrote a little bit of code to extract all the data from each of these variations and put them all into one pandas data frame, so which is like a table. And once it has that, it should be able to then plot the values for them. You can see that it's executing the post-processing code generation agent tool. So we should see somewhere in here the code. It looks like the plot failed, so it's gonna we have a debugging agent that is kind of checking out that the output is correct, and so in this case it's fixing it. All right, there we go. All right, so now you have all the variations that were present and the S11 magnitude versus frequency for all of them. But this is very easy to do actually in HFSS, so this is not really clear gain. So what I want to detail to you is what our vision is for this. Is maybe you don't know what is the right parameter value to achieve a specific goal, let's say a specific frequency of match. So you might want to do a coarse parameter search and then zero in the one that is closest to your target frequency, and then do a finer parameter sweep around that point. And so what you will write then is you will say run a parametric sweep for this parameter with this step size, then get all variation data, find where the minimum is closest to your desired frequency, and then run a parametric sweep there. So this is what I want to do right now. So imagine that we don't have this graph, and you want to say, so find the parameter value for DR that makes the minimum of S11 magnitude, evaluate at the frequency closest, and let's say to 2.45 to make it not obvious, because this design is for 2.4 gigahertz. So closest 2.45 gigahertz, and then run a parametric sweep with a finer step size, and the AI is going to automatically determine what that is around this value. And this is the idea, right? So you write this at the beginning of your workflow. You say, you know, run a coarse parametric sweep, find the value that is closest to my desired frequency, then run a finer parametric sweep around that point. And you can just go, right, and just let the agents do this process on their own. So let's wait, and let's make sure that the simulation gets run, and then we'll cut to when the simulation is complete. So since that takes a little bit of time. So right now it says, okay, it's going to start by finding the value, the DR value. We produce the minimum S11 at the frequency closest to 2.4 gigahertz. Great, that's perfect. So it wrote that code here. So the target frequency is 2.4 gigahertz, and it automatically find the minimum, the best R, and it says, listen, the best DR is for the value 0.25, and the frequency at that point is 2.436 gigahertz. And so now we need to find a parametric sweep around that point. And you can see that the simulation has started for that design, and the system has automatically generated that parametric sweep and is running it in the background right now. So if we go to HFSS, you can see behind my head that we have the simulation is running for it. And so we have automatically created a parametric sweep. And once that is complete, we can continue to extract. So I'll take a little break and I'll be right back. Okay, we're back. The simulation is complete for this new parameter sweep that you probably can find it here. There we go, yeah. And then let's go back to our tool and let's ask, for example, now plot S11 for all the new variations, created right just now, right? And so, okay, it thinks it's still running, but it's not, so I'm just gonna tell them, do it anyways, the values will be there. Okay, so we got the new data, and now it should plot the S11 for the new finer parametric sweep. Alright, it's calling the post-processing code generating agent. Alright, so now we have our finer value, and we can see then, and you can ask the final thing is like, get me the value, the optimal value, the R that achieves the closest match to was 2.45 gigahertz. And I know I've been doing this sequentially, but you can see if you set up a larger prompt that it kind of includes this whole thing in one go. This will basically execute it one by one. All right, there we go. So we have our best value for the R is 0.22, and then the frequency hit is 2.448. So super close with an error of 0.002 gigahertz. So excellent. That's all I wanted to show you. We are basically working on creating this capability of trying variation, extracting data, and getting insights from the simulations that are running, and then also connecting them sequentially so that you can run a large prompt and a large sequence and get your insights as you need them. Okay, thank you very much.